Have you ever asked a question so strange that the universe couldn't give a straight answer? Welcome to quantum computing, where reality breaks, logic twists, and possibility expands. You see, for over 70 years, classical computers have powered our world. They're fast, they're reliable, they run your phone, your car, your bank, even this video. And they all speak the same simple language: bits. A bit is either 0 or 1, off or on, like a light switch. Billions of these switches flipping every second. That's how classical computers think. But the universe doesn't run on simple switches. At its deepest level, reality is not 0 or 1, it's both, or neither, or something in between that doesn't quite make sense until you look away. This is where quantum computing begins. Not in wires or chips, but in atoms, in the rules of quantum mechanics, where particles exist in superposition, being in multiple states at once, where two particles can become entangled so that changing one instantly affects the other, even across galaxies, and where observing something actually changes it. This is the computer that breaks reality. So why does it matter? Because there are problems in nature, chemistry, cryptography that classical computers could never solve in a human lifetime. But a quantum computer might solve them in minutes. You're not just learning about a new machine. You're stepping into a new physics, a new way of thinking, a new frontier. This is the computer that breaks reality.
At the center of every quantum computer is a tiny miracle. It's called a qubit. Not a bit, a qubit. Quantum bit. Classical bits are binary, 0 or 1. One answer at a time. But qubits? They're tricksters. They can be 0, 1, or both at the same time. Imagine a coin. A normal bit is like showing heads or tails. A qubit is like spinning that coin in midair. It's not heads, not tails. It's everything in between. Only when you catch it, only when you measure it, does it snap into place. This is superposition, the strange ability of a qubit to hold all possibilities until observed. It's what lets quantum computers test millions of paths at once, not by brute force, but by quantum grace. But that's just half the magic. The real sorcery is entanglement. When two qubits are entangled, they share a state, no matter how far apart they are. Tangle one and the other reacts, instantly. Einstein called it spooky action at a distance. Quantum computers weave webs of entangled qubits, networks of uncertainty and probability. It's like building logic out of fog and shadows, delicate, powerful, beautiful. But there's a problem. Qubits are fragile. A whisper of heat, a flicker of vibration, even a stray cosmic ray, and the state collapses. The answer disappears. That's why building a quantum computer isn't just about clever code. It's about freezing atoms to near absolute zero, shielding them in vacuum chambers, and reading their states without destroying them. Today, we have a few dozen to a few hundred stable qubits. In the future, thousands, millions. enough to unlock chemistry, materials, medicine, and code breaking. Enough to make today's fastest supercomputers look like typewriters. Qubits aren't just quantum bits. They're quantum questions. And each one might hold the answer to a problem we can't even imagine yet.
So, we've built this delicate machine with qubits dancing in superposition, entangled like ghosts across space. But the question now is, what can it actually do? Let's be honest. Quantum computers won't replace your laptop. They won't run Netflix or play Minecraft. They're not faster at everything. They're faster at very specific things. Things where nature itself is too complex for ordinary computers to simulate. Chapter 1: Chemistry Reinvented. The molecules in your body, the proteins in a virus, the design of a new drug, they don't behave like Lego. They behave like quantum systems. That means classical computers struggle to simulate them precisely. Quantum computers, they speak the same language. With enough qubits, we could model complex molecules like caffeine or even photosynthesis from scratch. That could unlock new medicines, cleaner energy, or materials we've never dreamed of. 2. Cracking the uncrackable. Today's encryption protects everything: banks, governments, private messages. It relies on math problems that are really hard for classical computers to solve. But quantum computers could make short work of some of those problems. They can factor massive numbers with an algorithm called Shor's algorithm, a quantum trick that could, theoretically, break RSA encryption. That's why governments and tech giants are already racing to invent post-quantum cryptography, future-proofing security before the machines mature. 3. Logistics and optimization. From global supply chains to traffic patterns, from stock portfolios to delivery routes, we live in a world of optimization problems. Quantum computers could explore all possible routes at once, using algorithms like quantum approximation optimization. Imagine cutting delivery costs, improving factory layout, or managing energy grids with quantum logic. Even a small advantage in these areas is worth billions. 4. Machine learning on quantum steroids. Quantum computers can represent high-dimensional spaces naturally. That means they could enhance machine learning, finding subtle patterns we miss. We're just scratching the surface, but early research hints at faster training, smarter algorithms, and AI models that think a little more quantum. But here's the catch. All of this potential is mostly theoretical. Right now, quantum computers are noisy. Qubits decohere. Errors creep in. Scaling is hard. What we have today is called NISQ, Noisy Intermediate Scale Quantum. We're in the Wright brothers era of quantum flight. But we're making progress, fast. Google, IBM, IonQ, Rigetti, and dozens of startups are racing to reach the next milestone, quantum advantage. The moment when quantum machines can do something useful, better than any classical computer on Earth. We're not there yet, but the blueprint is drawn. The promise is real. And once the door opens, what we can do will change everything.
In 2019, Google dropped a bombshell. We've achieved quantum supremacy. What does that mean? In plain terms, quantum supremacy is the moment when a quantum computer solves a problem that a classical supercomputer can't, or at least not within a reasonable time frame. The problem Google's machine solved? Generating random numbers through a complex circuit. Not a useful problem, but one that would take the world's fastest classical computer 10,000 years to replicate. Google's quantum computer did it in 200 seconds. The world gasped. Headlines blazed. The quantum future is here! But not everyone was convinced. IBM clapped back. Actually, with a better algorithm, our classical computer could do it in just 2.5 days. Suddenly, supremacy sounded less like a revolution and more like a clever race condition. So, who's right? Well, both. Google showed that quantum computers could do something faster than classical ones, but the task had no real-world value. IBM showed that classical machines still have plenty of life left. The point isn't that we've won the quantum race, it's that the race has started. Quantum isn't magic. Let's clear something up. Quantum computers are not general-purpose machines that are better at everything. They're special-purpose machines that are better at certain kinds of math, probabilistic, exponential, highly entangled problems. That's why quantum supremacy doesn't mean the end of classical computing. In fact, they'll likely work together. Hybrid algorithms are already being developed, with quantum chips doing the weird math and classical chips cleaning up the results. Think of it like this. Quantum computers are telescopes for math, seeing patterns we can't with regular tools. So why the hype? Because the stakes are massive. Banks, biotech, governments, everyone wants first-mover advantage. Billions of dollars are pouring into quantum startups. Conferences, white papers, patents, prototypes. It's a gold rush, just not for gold, for qubits. But hype can cloud judgment. Companies claim quantum breakthroughs when they mean slightly better error rates. VC pitches exaggerate timelines. Tech influencers throw around quantum AI with little understanding. That's why it's important to separate supremacy from utility. So where are we really? We're in a delicate moment, past the first miracle, but before real-world impact. There's no true killer app yet. Error correction remains unsolved at scale, and most quantum tasks still fall within the reach of classical machines. If not now, then soon. But progress is steady. Companies are building 100-qubit machines. New materials like topological qubits are emerging. AI tools are helping stabilize quantum states. We're not in the promised land, but we're mapping the way there. Quantum supremacy was real, but narrow. Quantum hype is loud and often wrong. But quantum potential, that's still very much alive. It's not about conquering reality. It's about tuning in to the deeper layers beneath it and learning how to compute in the language of the universe.
Imagine trying to read a sentence while every letter is constantly changing. That's what it's like working with qubits. Quantum computers are powerful, but fragile. And I mean ridiculously fragile. Qubits don't just flip from 0 to 1. They drift. They wobble. They decohere. They get messed up by heat, vibration, light, even a nearby atom being in the wrong place. Bit flip? Try everything flip. In a regular computer, errors are simple. If a 1 flips to a 0, we just run an error correction check and fix it. Done. But in a quantum computer, A qubit can be in a superposition, part 0, part 1, and it can be entangled with other qubits. When an error happens, it's not just a simple flip, it's a full-state disturbance. You can't even look at it directly to check what went wrong, because observing the qubit collapses its state. So, how do you fix something you can't even measure without ruining it? Quantum error correction, the most complex band-aid ever. Here's the mind bender. We fix quantum errors without ever measuring the actual qubit. How? By using redundancy. Not one qubit, but many qubits to represent one logical qubit. Let's say one logical qubit equals 9 physical qubits. We use some for storing the quantum information and others, called ancilla qubits, to check for errors indirectly. They don't look at the main qubit. They look at how it affects entangled neighbors, like shadows dancing on the wall of Plato's cave. It's not just brilliant, it's quantum wizardry. The challenge: the more you add, the worse it gets. Here's the problem. Error correction isn't cheap. To build just one error-corrected qubit, we need dozens, sometimes hundreds of physical qubits. So, if we want a 1,000 logical qubit machine, the kind that could run useful quantum simulations, we might need millions of physical qubits. Right now, the best machines barely have 100. That's the Great Wall, the dark valley, the deep well we need to climb out of. So, what's the way forward? Some paths scientists are taking. Topological qubits, using weird particles called anyons to make qubits more stable, trapped ions and photonic systems, alternative ways to store quantum info with less noise, AI error correction, using machine learning to predict and fix quantum glitches in real time, and better isolation, extreme cold, vacuum chambers, electromagnetic shielding, entire rooms engineered to keep qubits alive for just a little longer. Each strategy is like building armor for a butterfly. Why this matters? Without good error correction, quantum computers are just noisy science experiments. With it, they become engines of discovery, accurate, reliable, scalable, ready to model new molecules, break new codes, and unlock the secrets of the universe. This is the bottleneck. Not building qubits, but keeping them alive long enough to do something extraordinary. We know how to do it, on paper. Now comes the hard part: engineering reality to cooperate.
Quantum computing isn't just a tech race, it's a geopolitical power play. This isn't just about solving math, it's about who controls the future of intelligence, defense, finance, and maybe even time itself. Welcome to the quantum arms race. United States, private power, public push. Google, IBM, Microsoft, Intel, Rigetti, IonQ. The US has the most diverse quantum ecosystem, billions in private capital, dozens of academic labs, DARPA and NASA backing research. Google's Sycamore proved quantum supremacy. IBM publishes roadmaps with real timelines, aiming for 100,000 qubits by 2033. Startups like PsiQuantum and Quantinuum are experimenting with different architectures, from photons to trapped ions. But there's friction.
IP is fragmented, coordination is loose. This is Silicon Valley. Everyone's racing, but not always together. China. Top-down, no limits. China sees quantum as strategic sovereignty. Their National Laboratory for Quantum Information Sciences is backed by billions. In 2020, the Zhejiang photonic computer claimed quantum advantage over Google's Sycamore. China's satellite QKD tests quantum encryption via space shocked the West. China isn't just building machines, they're integrating quantum into diplomacy, military, and cybersecurity. It's centralized, coordinated, and confidential. And it's fast. EU, precision, and partnerships. The EU takes a collaborative approach. Their €1 billion quantum flagship project unites research labs across Germany, France, Austria, the Netherlands. Strengths: fundamental physics, quantum networking, ethical frameworks. They're building quantum internets, quantum-safe encryption, and forging long-term alliances with universities and startups. Less hype, more rigor. Canada, the quiet giant. Don't sleep on Canada. D-Wave was one of the earliest companies to commercialize quantum annealing. University of Waterloo and Perimeter Institute are producing some of the best minds in the field. They focus on niche solutions, logistics, finance, AI-enhanced simulations. Quiet, focused, powerful. The risk: a quantum divide. Whoever cracks fault-tolerant quantum computing first could break today's encryption, could dominate next-gen AI, could simulate drugs and materials faster than any competitor. It's like inventing the atomic bomb of information. But here's the fear. What if one nation leaps ahead and locks the tech behind a national firewall? This is why quantum diplomacy is becoming a thing. Global summits, export controls, sanctions, espionage. It's not just a tech story, it's a security story, a philosophy story, a who will write the rules story. So, who's winning? No one, not yet. But some have momentum, others have money, a few have a head start. But the real winners will be the ones who solve two things: error correction and global cooperation. Because if quantum is about entanglement, maybe the future isn't about one country rising above the others, but about building a shared system, one entangled world.
Let's forget the hype. Let's talk usefulness. What will quantum computers actually do in the real world? Because for all the billion-dollar labs and glowing circuits, this story only matters if it changes something for you. Here's how quantum might touch our lives, sooner than you think. Drug discovery and molecular simulation. Every living thing, your DNA, a protein, a virus, operates through quantum chemistry. But our current computers, they can't simulate this accurately. The math, too complex. Even the best supercomputers approximate molecules. They guess. But quantum computers speak the same language as atoms. They could model a molecule down to the quantum level, helping chemists discover new antibiotics, create personalized medicine, understand diseases like Alzheimer's at their core, simulate proteins without years of lab testing. Pharma giants like Roche and Moderna are already investing in quantum R&D. Climate modeling and material science. Quantum computers could also help us model photosynthesis to create solar panels as efficient as plants, design new materials, superconductors, heat shields, biodegradable plastics.
simulate climate systems with far more nuance, especially chaotic ocean and cloud feedback loops. Why does this matter? Because the faster we understand nature at the subatomic level, the faster we can build sustainable tech to protect it. Optimization problems, logistics, energy, finance. Quantum shines in combinatorial optimization, where there are millions of possible paths, but only one best one. This is huge for logistics, delivery routes, shipping schedules, airport gate assignments, finance, portfolio balancing, fraud detection, and option pricing models. Energy grids, routing power efficiently across fluctuating demands. Companies like Volkswagen, DHL, Goldman Sachs, and ExxonMobil are all experimenting with quantum solutions. Why? Because even a 1% improvement in efficiency could mean billions in savings. Cybersecurity and cryptography. Here's the catch. Quantum computers are a double-edged sword in security. They could break RSA and ECC encryption, which protect 90% of internet traffic today. That's terrifying. But they also unlock quantum encryption, like quantum key distribution or QKD, which can't be intercepted without detection. So, the race is on. Governments are prepping for a post-quantum internet. New cryptographic algorithms are being tested right now, lattice-based, hash-based, code-based. Your future bank transactions, emails, and smart devices may run on quantum-safe protocols. It's a cybersecurity revolution and a race against the clock. AI plus quantum equals superintelligence? What happens when you combine quantum computing and AI? No one knows for sure, but the possibilities are wild. Training massive models faster, more efficiently, solving optimization problems for neural nets, speeding up reinforcement learning, using quantum pattern recognition to unlock new kinds of cognition. Some researchers even speculate that consciousness itself may involve quantum effects. That's controversial, but fascinating. It may not be Skynet, but it could be a different kind of intelligence, one we don't fully understand yet. So no, quantum won't make your smartphone faster, it won't replace your laptop, and it probably won't cure death. But in the background, in labs, in models, in molecules, it might quietly reshape the foundations of how we build, compute, cure, move, and secure everything. Not science fiction, just science that finally speaks nature's native language.
Is your mind quantum? Not just your brain, the firing neurons, the electrical circuits, but your consciousness, that flicker of you-ness, that presence behind your thoughts, the voice you're using to read this right now. Could it be quantum? The classic model, brain as machine. The dominant view of neuroscience is this: the brain is a biological computer. Billions of neurons fire in patterns. Electrochemical signals create thoughts, emotions, awareness. It's complex, sure, but in theory, all classical. This is known as computationalism. Your mind is what your brain does. But enter quantum weirdness. Quantum mechanics deals with things like superposition. A particle exists in multiple states at once. Entanglement. Particles affect each other instantly, across distance. Collapse. Observing a system locks it into one outcome. These are strange enough in physics, but some thinkers have asked, could consciousness require this strangeness? The Orc-Or theory, Penrose and Hameroff. One of the most famous and controversial quantum consciousness theories is orchestrated objective reduction, or Orc-Or. Roger Penrose, legendary physicist, argued that human understanding, especially of math and meaning, can't be reduced to algorithms. Something deeper is at work. Stuart Hameroff, an anesthesiologist, had a hunch. Consciousness might arise from quantum processes inside neurons, specifically in structures called microtubules. Together, they proposed consciousness emerges when quantum superpositions in microtubules collapse in a specific way, influenced by gravity, producing a moment of awareness, a quantum click in the fabric of reality. Each conscious moment is a tiny quantum event. The skeptics. Most neuroscientists aren't convinced. Critics argue that the brain is too warm and wet for quantum coherence. Decoherence would destroy any delicate quantum state. There's no evidence that microtubules behave quantumly. Classical neuroscience explains most cognitive functions already. Even Penrose admitted his theory is speculative, but deliberately so. He believes conventional physics can't explain consciousness. And maybe that's the point. Quantum entanglement and meditation? Still, some experiments hint at something strange. EEG studies of meditators show unusual coherence patterns. Some researchers propose entanglement between brain regions. Others ask, if particles can remain entangled across space, could minds? This doesn't mean telepathy is real, but it nudges us towards a deeper question. Are we truly isolated individuals, or part of a vast, interconnected quantum field of experience? Science meets mystery. Quantum consciousness isn't proven. It may never be, but it forces us to wrestle with the limits of explanation. If a computer mimics the brain, can it ever be conscious? If we reduce the mind to matter, do we lose what makes us feel alive? Or does consciousness hint at something deeper, entangled with the very structure of reality?
Quantum computing isn't just a new kind of machine. It's a mirror. A mirror that reflects not only the strangeness of the universe, but the limits of our imagination. For centuries, we've chased better tools, levers, engines, transistors. Then came AI, now qubits. But quantum computing is different. It's not just faster, it's fundamentally alien. It runs on principles that contradict our common sense. Superposition, entanglement, interference. Not on or off, but both. Not certainty, but probability. The new digital divide? And that makes us ask, are we building something we truly understand? Quantum computing could crack our encryption, reinvent drug discovery, optimize logistics, finance, energy, accelerate AI. But it also introduces a new divide between those who understand the quantum world and those left behind. Will quantum power be democratized or monopolized? Will it heal the planet or deepen inequality? A choice at the threshold. Every great leap in history comes with risk. We split the atom and got both nuclear energy and nuclear weapons. We mapped the genome and now debate the ethics of editing life. We built the internet and now struggle with misinformation, surveillance, addiction. Quantum computing is another threshold, a doorway to unimaginable opportunity and profound responsibility.
This was Mindwaves After Dark, where complexity meets curiosity. If your mind is still buzzing, good, sleep on it. The future's just beginning. Follow, share, or rewind anytime.
See you in the next paradox.